Okay, welcome to our second lecture in the Traffic Operations and Management course. We will revise what we discussed last week, and we will try to have some hands-on experience with solving some problems. We are not going to iterate on this, but I'm going to iterate on this first, that we have a quiz on the week of February 7th. Okay, this is going to be, I think, let me just update this date. So now, since we have agreed on a time for the class, so this is going to be on February 9th. And this will be on March 21st, so March 23rd. Okay, so just keep note of these dates, please. Okay, our first module focused on grade separation and interchanges, and weaving segments. So the first part we discussed the grade separation and, to be specific, the interchange layouts. For the interchange layouts, we discussed the warrants for grade separation. Okay, that in case we do grade separation in case we have two or more uninterrupted freeways facilities intersecting together, and in case where an uninterrupted freeway facility intersects with a regular interrupted facility. Okay, so these are the main the main cases that we build an interchange. What is the principles of separation methodology? Okay, for all movements with crossing points of conflict, okay, each movement will have an elevation level such that all crossing points points of conflict are eliminated. Okay, يعني هنا to be specific, read this part. Okay, it says for all movements with crossing points conflict, okay, all these must be eliminated. Crossing point of conflicts must be eliminated. That's our goal or our separation strategy. Okay, merging and diverging points, there is no problem with it. يعني هنا merging it's okay, with diverging okay, are allowed, but crossing points, these are not allowed. You understand with me? And if I have a movement like this, left turn, I have a through movement. This is a crossing point of conflict. This is not allowed in an interchange. However, merging points, that means I have a right turn, it can merge with a through movement. Or I have through movement, we can have divergence here. So this is divergence. Here we have a merging, okay? Those are allowed. But this one, it's a big no-no, okay? This is not allowed at all. So that's why, if you can see here in this interchange, how many levels do we have? We have level for this movement. This is one. A second level down here. Then there's a third level here, below all of this. Okay? And probably underneath, there is a train here. or there is a railway. So you can see that there is multiple levels of the, that depends on the complexity of the interchange itself. Okay, what do we need with crossing points? These are the crossing points. All the points here are crossing, okay, are cross points, cross points of conflict, okay? So the first step that we make a, level separation. We separate the through movements on both directions into two levels, okay? By doing this, we only left with these points, only those 4 points. Those 4 points are generated by what? By the left turns in the movements, okay? So these are the left turns from the intersection, okay? Those are the 4 points. Those 4 points we cannot eliminate with this grid separation. We need to have a special treatment for these left turns, okay? So the first strategy okay, here, these are the right turns, as we mentioned before. So the merging and the diverging are okay, but what we are left with are the left turns. So there are 3 ways to deal with the left turn. For example, here, if the left turn volume was, less than or equal 1200 vehicles per hour, then we just do the indirect, which is to have the left turn volume going past the grid separation, then goes underneath, okay? This usually makes for us what we call clover leaf interchange. You know what's clover leaf? ورقة البرسيم. Like this one. What that?
الوردة اللي تكون في الهاي واي.
Could you just raise your voice?
يقول دكتور هذه اللي تكون الوردة اللي في الهاي واي المخرج.
Yes, but there are different strategies for this. The common that we know or that we see is, we call it clover leaf. This configuration is clover leaf. Clover leaf is basically, it resembles the leaf of the clover. ده بنسميها ورقة البرسيم. عارف البرسيم؟
اوكي دكتور.
Okay. So this one, usually we go to this, we call this kind of treatment for the left turn indirect left turn. It's not direct left turn, okay? So here, and usually we go to the indirect left turn if the left turn volume was 1200 vehicles per hour, okay, or less. The advantage of this, it's low right of way and low cost. The cost is negligible because basically you don't have any new structures. You have already one structure here. You have one bridge, that's it, okay? And that's a typical view for a cloverleaf interchange. Then that's also another cloverleaf interchange. What if the volume was high? If the volume of the left turn was between 1200 and 1800 vehicles per hour, okay? Let me just reiterate on there is disadvantage in the clover leaf. Why? The clover leaf, it has a small radius, here. So the small turning radius dictate lower speed. Okay, so the lower speed, it means lower flow rate. Okay, so but if we have a higher volume, then this approach is not recommended. We go to the semi-direct left turn. The semi-direct left turn, basically the left turn goes this way, then goes across, on top of the through movement, then it goes down and merge with the other through movement. The advantage, it needs moderate right of way, okay, better capacity and speed. You don't kill the speed here. The disadvantage, cost. The cost here is higher because you have to make another structure in this area. Clear? Okay. So that's, this configuration, we call it the turbine interchange. In this configuration, all left turns are treated as semi-direct. Okay, as you can see here. So when you build this, it takes that shape, the turbine. Okay. So that's an example for an indirect treatment. The left turn, went this way, then went across then across the through movement. That's the through movement that came with. Okay.
دكتور
Yes.
في أمثلة على التوربين عندنا هنا في الشرقية.
I don't think so. I think I haven't seen it here in the Eastern Province. So that's another example for the semi. That's what they call the turbine interchange. As you can see here, how many bridges do we have? That's the main initial bridge, which is separating the through movements from both directions. But now we have another bridge here, another bridge here, and there's another bridge here, another bridge here. How many bridges? Okay, we shall continue here. As you can see in this turbine interchange, it's all the four left turns are treated as semi-direct, as you can see in this one. What is the difference? When we mention that's the main structure, okay, which is a great separation for the four through movements, okay? The right turns are here. We have right turn ramp here, right turn ramp, and so on. For the left turns, how many bridges additional we need? We needed 1, 2, 3, 4, 5, 6, 7, 8. So here they added 8 additional structures to the main structure. Okay, of course, this means a lot of cost, a lot of money. Okay, this one here, they consolidated some of these bridges. So for example, here that was one bridge, here another one bridge. So they made 4 bridges to serve the 4 left turns. Okay, and I think this one is in UAE, in Emirates. This one is in Dubai. Okay. Okay. Sometimes you might make the semi-direct in case of a T intersection, that we have a T interchange. The last strategy, okay, which is the direct left turn. Direct left turn, it's typical when we have volumes that exceeds 1,800 vehicles per hour. Okay. Remember, that was the semi-direct. How many grid separations we made here? We made 1 for the main movement, for the through. Okay, then this another bridge here. But here you have to build the main bridge here, for the through movements. Then there's another elevation here for this left turn to be above the opposing through movements. Then another bridge here to go over the other direction through movements. Then it merge here. Okay, of course, this is more expensive and it costs much higher than the previous two alternatives. And that's the configuration of the direct left turn.
دكتور ريكورد بليز مو شغال الريكورد.
Recording. Thank you. Okay, this one, as you can see, that's an example for an implementation for, but I think this one is more of, I think semi-direct or direct. It almost, I think this one should be treated as a semi-direct, not direct left turn. I'm wrong here. This is not direct. This is semi-direct. In this example, you can see that not all left turns are treated this way. Only two left turns here, direct left turn, but the other direction, it has an indirect left turn. Why we did this? Because basically they have done this because the traffic volume, there was no need for the traffic volume to have a direct left turn. So that means in an interchange, you can have a mix between different configurations for left turn treatment. You can have an indirect, you can have semi-direct, you can have direct, all in the same interchange. For example, here, okay, you will see that the left turn from this approach is treated indirect, but the left turn here treated as semi-direct. Okay, let's have an example on this. Okay, we're going to start with this example. What volumes do we have here? Okay, the criteria basically less than 1200 vehicle per hour. Okay, and from 1200 to 1800 vehicle per hour. Then greater than 1800 vehicle per hour. Okay, so in this case, we put the indirect. Here we put what?
Doctor, we can't hear you, Doctor.
You can't hear me? Can you see the screen?
Yes.
Okay, here that's semi-direct, and this is direct left turn. Okay, so in our case, let's start, and from here we make, so that's this volume, and here so this volume is done. What we are left with? We're left with this left turn and this left turn. Both volumes are what? less than 1200. So the connection will be what? Will be indirect. That means those coming from this, for the 950, they are gonna go this way and come this way. And those so those are the one for the 950. Those for what؟ قلنا ايه يا شباب؟ قلنا هنبتدي بالثرو موفمنتس ونديهم كده. يبقى كده خلصنا من الثرو موفمنت. وبعدين قلنا الرايت تيرنز ايه نرسمهم لوحدهم اهو. اوكي. فكده الرايت تيرن دي خلصنا منها والرايت تيرن دي خلصنا منها. فضل معانا ايه؟ 950 وال 815. واضح؟ في مشكلة في الصوت يا شباب؟
حاليا لا يا دكتور، واضح.
واضح دكتور.
ممتاز. طيب يبقى هنا نبتدي let's focus on the 950 vehicle per hour. This left turn for. We make an indirect left turn that will go this way and merge here. Okay, so this way. Why we did a indirect left turn? Because this volume is less than 1200 vehicle per hour. For the 815, okay, which is from this, okay, it goes all the way this way, then it make a left turn, okay, and here we build a bridge. So let me just try to, oops. Here we build a bridge. Of course, this area should be okay. كلير يا شباب؟ يبقى احنا كده حولنا الموفمنتس بتاعتنا، تمام، كلها covered. بقى في great separation. الليفت تيرن اللي من هنا طلعت اوكي ولف من هنا ومشى من تحت الكوبري. the other left turn went from underneath the bridge going up ramp, okay, and coming this way. So that's the case of an indirect but here, for example, let's look at this case. This case is kind of similar, but there is a difference. What is the difference? We will start first with the two through movements. Okay, so this is for the 2, 3, 5 vehicles. And this is for the 1120 vehicles. Then we go with the right turn. So the right turn here, that's 835, we are done with. And we have here that's the 650. For the 950, we go again with a, indirect left turn. This way. So it goes from underneath the bridge, going over the bridge. But this one doesn't work. Why? Because it's greater than 1200. So it's between 1800 and 1200. Okay? So this will go this way. Okay? And there's a bridge over here. So those are for the 1415. This is for the 950. And of course, clear يا شباب. So those were basically simple. Okay. Okay. So in both examples, we just shown how an indirect, okay, and semi-direct, and so on. So that's how we structure the interchange layout. Any questions so far? Okay. This is another example for two movements or two left turn movements that are treated differently. So you can see here that this one is an indirect, sorry. This one is an indirect, and this one semi-direct. This type of interchange, we call it usually the trumpet interchange because it's similar to the trumpet. Sometimes if we have a freeway crossing over a street or other interrupted facilities, we can just have a roundabout underneath to deal with the left turns. You see, like this one. I think this one is in Kuwait. I think this one is in Kuwait City or in Abu Dhabi. I'm not sure. So that's a freeway, and this is a street in the downtown. Okay, so we have a roundabout to treat the left turn movements, and of course we have traffic signals underneath here. Any questions? Hello.
ان شاء الله واضح ان شاء الله.
لا يعني دلوقتي في مشكلة تاني في موضوع الصوت، ولا الصوت ماشي دلوقتي؟
لا الآن واضح.
هو في الغالب كان السوفت وير اللي كنت بشتغل عليه التاني هو اللي كان عامل مشكلة، اللي هو سوفت وير اسمه وايت بورد، مايكروسوفت وايت بورد. اوكي. طبعا as we mentioned earlier, these interchanges, there is always weaving that occurs at these interchanges. Okay, and these interchanges result in generating weaving segments. Okay, so for example here, let's have a look at this one. Typically what we end up with traffic coming from this direction, and they want to go through, and some wants to make They want to merge to the main road, and some wants to exit to make a U-turn, for example. In the meantime, we have traffic coming from this way, and they want to go through, and in the meantime, other volume wants to exit. So this creates a situation, if we can plot it this way. So this is what we call weaving segment, okay? Of course, the same situation will occur in this area because we have vehicles coming from the ramp. Some they want to go all the way here, some wants to go off to the other ramp. In the meantime, you have traffic going through and wants to continue, and also another traffic that wants to exit. So there is this situation will occur. So that's what we call weaving segment. So how can we determine the weaving segment level of service? We mentioned that the weaving segment level of service is based on the density, okay, calculated based on the density of the traffic in that segment, okay? And the highway capacity manual, okay, it has 5 distinct components in the methodology. First of all, the model predicting the space mean speed, the average running speed in the weaving segment. Then we calculate the model describes the proportional used of lanes by weaving and non-weaving vehicles. There's an algorithm that converts predicted speed to an average density. Then definition of level of service criteria based on density. We mentioned that before that, you know, if the density less than 6, then it's level of service A. If it was a freeway weaving segment, if it's a multi-lane or and collector distributor weaving segment, then it's less than A. For level of service B, the density should be between 6 and 12. Here between 8 and 15, between and so on. Any questions? Then, in order to, you know, we have these notations. So if we have, you know, 2 approaches A and B, then we have here V out. You know, these either V out 1 or V out 2. And here it's V out 1 or V out 2. And that's what we call the weaving volume. The V out 1 and V out 2, those are through volumes or through traffic. So here that's VW1 or VW2. Here also either VW1 or VW2. What determines whether it's 1 or 2, it's the magnitude. So the higher will get V1, VO1. Then we have L, that's the length of the weaving segment. Okay. Then we have, hold a second. Then we have N, that's the number of lanes in the weaving segment. Then we have N weaving, that's the number of lanes to be used for weaving, NW. NW max, that's the limit or the maximum number of weaving that can be allocated for weaving in that segment. Okay. NW, that's the number of lanes used for non-weaving vehicles. V, that's the total volume. In order to have a better understanding for this, let's start working. Okay. Let's work an example and see how we can, you know, deal with this. Or let's try to solve this example. نحل هذا المثال يا شباب. اوكي. وهنا احنا عندنا weaving segment length. هنقول ان اللينث بتاعنا كان في الاكزامبل ده كان 250 meters. اوكي. اول خطوه بنعملها ايه؟ اول شيء نعمل let's do some calculations. يعني ده هنا في اوت 1 في اوت 2 في non waving هيساوي كام؟ 1215 بلس 245 هيساوي كام يا شباب؟ حد يجمع معايا؟ 0 6 4 1
1460.
V weaving equals 478 plus 245 هتساوي هنا 3
483
كام؟
483
483
ايه
لا I think غلط I think 7 اوكي
اي صح عليك 723
723.
okay this makes sense and this is passenger car per hour and this is also passenger car per hour. هنحسب في عندنا ريشيو المفروض ان احنا هنحسبها. خلينا نطلع كده ونشوف ايه الريشيوز دي. في عندنا في ار اللي هي الريشيو بين الويفنج والتوتال فوليوم. اوكي so let's go back. في توتال كام؟ هتساوي 2183 passenger car per hour. الريشيو قلنا كانت ار في ولا في ار؟ فوليوم ريشيو. طب كويس. هتساوي كام؟ الويفنج فوليوم 723 divided by 2183 هتساوي 0.3 كام؟
31
0.31 ممتاز.
331 عليه 331 يعني بعدها 3 و1 بس.
حياك الله ممتاز. طيب محتاجين ايه تاني؟ تعال نشوف الميثودولوجي بتقول لك نحل ازاي. الميثودولوجي بتقول لك اول حاجه بنعمل فوليوم ادجستمنت عشان نحول الفوليوم الى باسنجر كار. لاحظ هنا احنا شغالين في من الاول باسنجر كار فوي دونت هاف ا بروبلم كل اموركم طيبه. طيب بنعمل بعد كده الحسابات اللي احنا وريناها لكم ده عملناها اوريدي. بنشوف determine the weaving segment configuration. weaving segment ده configuration B ولا A ولا C ولا ايه نوعه. فنرجع تاني ركز معايا هنا. خليني بس دي اكبرها شويه كده. طيب خلينا نشوف لو في سيارة ماشية هنا if we have a car driving this way it must make one lane shift in order to go to make that weaving. So that's for the 360 that's what they are gonna do. So how many lane shifts they have done?
2 lane shift
2 lane shifts. But for
Type C.
the other direction 478 okay let me just change the color. They can just go here, keep going. How many lane shifts they did? 0. Okay, let's go back to our table. So we have 2 and 0. So we have 2 and I'm sorry, 2 and 0. So this is type C. So the type that we have is what, Shabab?
C.
Okay, then we have here C. Okay, that's good. So what's next? The next, we calculate the weaving intensity in order to determine the speed for the non-weaving and the speed for the weaving. Both equals how much? Equal 24 . So here we have 24 plus the speed of a free flow minus 16 divided by 1 plus W non-weaving. Here will be 24 plus speed of free flow minus 16 divided by 1 plus weaving intensity for weaving. Okay, let's say that the speed of free flow here was 100 kilometers per hour. Okay, so now we want to get the values for the weaving intensities. How we can get the values for the weaving intensity? We get the value for the weaving intensity through this table. Yes. So here for the weaving for the weaving traffic, okay, we take this column and we have type configuration C, so we go with these values. Okay, these are the values that we are looking for the weaving speed. For the non-weaving traffic and the non-weaving speed, okay, we will go with this. As I mentioned, we will assume that it's unconstrained. Clear? Let me just take this with us and let's go back. Here. So the weaving, let's do the calculation here. The weaving for non-weaving equals A, okay. So here this equals how much? A multiplied 1 plus 1 minus VR, blah, blah, blah. Okay, so here we have 0.0020 multiply 1 plus VR. How much was VR? 0.331. So it's 1.331 to the power 6 here. B, multiply the volume. How much total volume do we have? $2100. الفوليوم اللي عندنا كان كام يا شباب؟ 2183 divided by, okay, how many lanes do we have? Go here. 1, 2, 3, 4. Divided by 4 to the power. How much power do we have? 1.1. Then we divide all of this by how much? The denominator, 3.28, multiply 250, that's the length, and to the power 0.6. Can someone please make the calculation for this? Let me-
0.203.
How much?
0.203. 0.203.
Excellent. And the weaving for the weaving traffic equals 0.08 multiply 1.331 to the power 2.3 multiply 2183 divided by 4 to the power 0.8, and in the numerator and the denominator will be 3.28 multiply 250 to the power of 0.6. This equals
Equals 0.426.
excellent. Okay, then let me just put this one aside here. Let's now calculate the speeds. So we have 24 plus the free flow speed, we assumed it to be 100. So we have 100 minus 16 divided by 1 plus weaving intensity for non-weaving, which is 0.203 equals, and here 24 plus 100 minus 16 divided by 1 plus, I'm sorry, I mixed it. No, I didn't mix. That was correct, no problem.
$93.825.
How much here?
93.825.
0.825 kilometer per hour. And here it's 100 minus 16 divided by 1 plus 0.426 equals
82.906.
82.906 kilometers per hour. Perfect. Are we done? No. After calculating the speed, we have to go and check to see the mode of operation. Are we operating, constrained or unconstrained? So we have to go here. Okay, no, that was not this one. Not this one. Not this one. Yes, determine the type of operations. Okay, to know whether we are operating under constrained or unconstrained conditions. So we go to this table. In this table, what we need for type C is this equation only. So we are going to copy it and just drag it with us. And we are going to just keep it temporarily with us here, but we are going to eliminate the parts that we don't need. Okay, so we are just using this part. So let's calculate the N weaving. How much do we need? So it starts with N. How many lanes we have? We have 4 multiply 0.761 plus 0.047 multiply how much? VR 0.331 minus 0.0036 multiply 250 minus 0.0031 multiply the difference between the non-weaving and the weaving. So the non-weaving is 93.8 minus 82.9 and close the bracket. How much do we have here?
2.61.
2.61. The maximum N weaving, maximum equal 3. So in our case, N weaving is less than N weaving max. So it's what? Unconstrained. مفهوم يا شباب؟ Is that clear? Okay, so what's the next step? The next step now is to calculate the density and estimate the level of service. So how can we estimate the density? Let me just, okay. Please just keep record of these values. First of all, we have to calculate the average speed. Okay, V average or S average equal the total volume divided by the V non-weaving divided by S non-weaving plus V weaving divided by S weaving. So this will equal to, how much volume did we have? The volume was 2183. So here we have 2183 divided by non-weaving for 1460. So it's 1460 divided by, what was the speed? 93.8. 93.8 plus the weaving volume was 723 and 82.9. 723, 82.9. How much? The average now. شباب
more conductor.
$89.88.
89.885.
بالضبط.
89.85
No,
kilometer.
Dr. 885.
Okay. This is a correct number or correct value. Why? Because it's between those values. The value here must be between the non-weaving and the weaving. Okay? So now we want to get the density. So the density will equal to the volume divided by N divided by S bar. So we have volume 2183 divided by 4 lanes. And here we divide by 89.885. How much is the density?
6.
So the density is 6. What are the units? Passenger car per lane per hour. So the level of service almost 8.
ما يعتبر قليل دكتور.
نعم.
ما يعتبر قليل 6 car.
Yes. 6 cars, it means that the level of service is very good. And remember here, the free flow speed was how much? 100. So because of the and you have here, you know, the total volume is 2183 and you have 4 lanes. That means without the weaving segment, you have 500 vehicles per lane. You get that, Sanad?
Yes, Doctor.
Also, if you look at the weaving intensity here, these values are low. Okay? And even if you look at the volumes, 360, and look at this configuration, I don't think there's an issue with that. Clear, Shabab? But it's good that you question the values or the number that you get. But when you look at the values, look at what you have here. Because here, as you know, the non-weaving is 93 speed, and here it's 82, weaving intensity 0.2, 0.4. These are fractions. You start worrying when you get into the you know, the constrained case. When we have a constrained weaving segment, that's when, you know, things gets ugly. Okay.
Okay.
Okay. Okay, Shabab. Thanks. And let me just take. I'm gonna just end the recording here.